So now we're going to look at the solving of absolute value equations, both algebraically and graphically. When you're solving algebraically, you will always use the definition of absolute value, which says that the absolute value of a positive value is that value itself. So if x is positive or 0. And if you're taking the absolute value of a negative value, then the output will be the negative of that negative value to make it positive. So the solving of absolute value equations involves breaking your expression into pieces. So here's a simple absolute value equation. Let's break it into its two pieces. So we have to consider where the inside is positive and where the inside is negative. So case 1, when the inside is positive, 6 minus x is greater than or equal to 0. That would mean that 6 would make it 0. So if x was actually less than 6, the inside would be positive. Okay? And therefore, the absolute value of something positive is that expression itself, equaling 2. The other case to consider is when the inside is negative. Now this depends on the values of x I'm talking about. So the inside is negative if x is greater than 6. And that would then make my equation the negative of that inside expression to equal 2. Alright, so I've broken my original equation down into two separate equations without the bars. I can now solve, and if I do that, I'm going to get x equals 4 here. Now what I want to do is make sure that x equals 4 is within this range. Is x equals 4 less than or equal to 6? Yes, it is. So that should be good as part of my solution. And negative 6 plus x, I would add 6. X is 8. This should be good as long as x is greater than 6, which it is. Alright. Now absolute value equations can get complex, so I would always encourage you to check your work by substituting back into the original equation, because as you're going to see, sometimes there are extraneous roots. That's roots that solve out but don't actually work when you put them back. So if you put 4 in here, 6 minus 4 is 2, the absolute value of 2 is 2, yes. And x is 8, 6 minus 8 is negative 2, the absolute value of negative 2 is 2, and so both of these are valid solutions. So I've solved that algebraically. And then to solve graphically, remember, we've done solving graphically with many types of equations before. This involves one of two ways. What I'm going to do here is I'm going to enter both of these equations as two separate functions. Y equals absolute 6 minus x and y equals 2 into my calculator. Alright, so y equals math, number, absolute value, 6 minus x. And the second function is 2. Graph my two functions. And the x coordinates of the points of intersection should be my solutions. So second function, intersect. Used this button before. X equals 4 is one solution. And the other one, and x equals 8. Okay, so I confirm my solution. Alright, let's make things a little bit more complex. This time let's solve graphically first. So I'm going to enter my two functions, x plus 5 and 4x minus 1. If I graph, I get what appears to be one solution right there. X equals 2 is my solution. If I plug back in here to see if this works, 2 plus 5 is 7, absolute value of 7 is 7, and on the right side 4 times 2 is 8 minus 1 is 7, so that works. Now let's see if we can solve it algebraically. So to solve algebraically, I have to consider when the inside is positive and when the inside is negative. So case 1, if the inside is positive, if x plus 5 is positive or equal to 0, That will happen when x is greater than or equal to negative 5. And then my equation would be the inside as it is, because it's a positive value, so the absolute value of the positive value will be the same as what's inside, equals 4x minus 1. And my other situation, case 2, is when the inside is negative. And the inside is negative if x is less than negative 5. And so my equation would then be the negative of the inside negative. And here's my equation to solve. So then we're going to proceed to solve. And when we get our solution, we have to make sure that our solution is in the indicated interval that we're using. So I'm going to get 6 equals 3x, and so I'm going to get x equals 2. And is 2 greater than, if I go back up here, 2 greater than or equal to negative 5? Yes, it is, so that should be a valid solution. In case 2, I'm going to solve. X equals negative 4 over 5. Is the x value I get less than negative 5? Actually, no, it's not. Okay, so that gets rejected. It's an extraneous root, and so we can see that we're back to just the one solution. So there's an example of an absolute value equation that gives an extraneous root. Okay, here's another example. I'm going to just rearrange this equation. I'm going to move the 9 to the other side. Now what you should always do when you're doing something mathematically is just to try to think about the situation and what's going on. If I look at this, some of you might see that if I'm absolute valuing something, whether positive or negative, what I'm going to get is a positive value. And here it's saying I'm going to get a negative 7, which is not possible. So right away, without doing any work, just by inspection, I know there's going to be no solution. Okay? If you don't believe it, let's solve it graphically. Now, what I'm going to do to solve this one graphically is I'm going to do something a little different this time. Is I'm going to set the whole expression to 0. So I'm going to minus the 2 over to the left, so that's plus 7 equals 0. And then I'm going to graph y equals this. And any potential solutions should be x-intercepts of the graph. So if I do my graph, I see it's up here. Where does y equal 0? It never does. There's another indication. There's a graphical indication that there is no solution. All right, another equation with another level of complexity in here. We now have a square involved. So let's look at this graphically. I can enter two equations and see where they intersect, or I can set it to 0 and make one function, y equals that, and see where the x-intercepts are. This will tell me what my solutions could be. Alright, so absolute value x squared minus 3x minus 2. Graph that, and it looks like I have 4 solutions. Wow. 1, 2, 3, 4. Could use my 0 button to get them. Okay, something between 0 and negative 1. It looks like there's 2 solutions here. The graph's going up and coming down, and then there's another one there. Let's just find one of these just for now, just so we can see. Press the 0 button. I'm trying to find the 0 on the left. Move it to the left of the 0, to the right. Enter. So negative 0.56 looks like maybe an irrational number, and decimals go on probably forever without a pattern, but the algebra will tell us what's going on. Now the thing that makes this question a little bit more complicated is that the inside is a quadratic, so I can factor that. And I'm just going to go off on the side here, and I'm going to think of the graph x times x minus 3. I know that that would be a parabola with zeros of 0 and 3 opening up And so the function inside would be positive when this graph is above the x-axis. Okay, so case 1 is that the inside is positive when x is 0 or less, or 3 or greater. And I know that just by looking at the graph of this function itself, which is a parabola. Okay, case 2, this is a y value. The y values in the graph are negative in this section. So the inside is negative when x is between 0 and 3. Alright, so we've got our two situations mapped out, our positive situation on the inside and our negative. And so when it's positive on the inside, the absolute value of the expression is equal to itself. And when it's negative, it's equal to the opposite of itself. Alright, so we have two equations to solve, and both are quadratic equations. So over here we can set our equation to 0, and I thought that might be an equation that would factor, but it doesn't. So it's going to involve the quadratic formula. So the opposite of b, 3 plus or minus negative 3 squared minus 4ac all over 2 times a, which is 3 plus or minus the square root of 9 plus 8 over 2, which is x equals 3 plus or minus root 17 over 2. Alright, and those are a little bit complicated to plug back into my original equation, so I'm just going to wait on that. I'll come back and check the validity of this later, because remember, you need to check absolute value equations. Things you solve for may not actually work out in the end. But we did look at the solution graphically originally, and we saw 4 solutions. So let's see what happens over here. Distribute the negative. And so 0 equals x squared minus 3x plus 2. Looks like we're spared another quadratic formula because this factors. So x is 2 or 1. And let's just jump back to our graphical solution. And was x equals 1 one of the solutions right there? Looks like it was. Let's just see if it is. If x is 1, y is 0. If x is 2, y is 0. I've verified those very quickly. And these other two must be the root, the values of the root, this root, which we calculated one of them to be 0.5 something. Can't remember what it was, but let's just type this in and see. 3 plus root 17. $3.56. And the other one, there's that number we verified earlier. So 4 solutions, all of these satisfy the original equation.